Hello everyone! The purpose of this lab was to observe the force of drag on a swim cap falling from rest and then compare the observed position and corresponding time of the falling swim cap extracted from tracker to Python models predicting the trajectory of the falling swim cap. Here you can see where I uploaded my video into tracker. I observed frames 96 through 113, the point from which the swim cap is initially leaving my hand up to the point where the swim cap makes first contact with the ground. I set my calibration stick to a known length, my own personal height of 1.677 meters, and I set the origin at the base of the swim cap position during the initial release. And here you can see where I compare my two sets of Python codes. The initial conditions are the same between the mass and the initial position, initial velocity. However, the proportionality constant for the magnitude of drag force differs. I ignored that in my model, not accounting for the force of drag. However, within my Python code accounting for the force of drag, I set this constant to a number that allows the model to approach the observed displacement in the y direction. I kept my delta t at a small time step to maintain accuracy of the iterative calculations. And within my Python code for the model not accounting for the force of drag, I set my net force to the weight force, whereas with the Python code for the model not accounting for the force of drag, my net force was a summation of the weight force and the drag force. Here are my models. The model for not accounting for the force of drag infers that the swim cap is falling at a slower rate than in reality. And this is because the predicted final position is less than the observed final position, while the duration of the fall is held at a constant time. If our time is constant and we have a decrease in the y displacement, then there would also be a decrease in the y component of the average velocity. Again, within my models accounting for the force of drag, it infers that the swim cap is falling at a slower rate than in reality, for the same reasons. The force of drag appears much larger than in reality, represented by the blue arrow, because the vector was multiplied by an arrow scale of 200 to allow the vector to be visible. Here are the conglomerated results. As discussed earlier, the observed position exceeds both modeled positions, and the force of drag was so minute that the model not accounting for the force of drag is masking the curve of the model accounting for the force of drag. What does it mean? Well, we can see here that the observed final velocity equals -3 meters per second, and this was calculated from the y displacement over the change in time of the last two coordinates. The swim cap appears to approach terminal velocity because the slope becomes less steep due to the decrease of the change in velocity. However, more data would be needed to determine whether terminal velocity was reached. Terminal velocity in a position versus time graph is when the function becomes linear, which is due to the slope, which is the velocity, becoming constant, and thus the change in velocity is decreasing. What if the initial velocity was not zero? The time duration for the object to fall to the ground and the time interval needed to reach terminal velocity would be less. However, the magnitude of the terminal velocity would not be affected because terminal velocity in this situation is determined by the force of gravity and the force of drag. And here are models accounting for the force of drag that did not start from initial velocity of 0. Instead, I set them at initial velocity of -1 meters per second. And this model predicts that the object would be falling at a faster velocity for each corresponding time segment. And we can confirm this by comparing the final velocities. The observed data shows the swim cap falling a greater distance and thus at a faster velocity than the model data, which is not possible. There is one possible explanation though. While tracking the descent of the swim cap, it was difficult to determine at which frame the swim cap made initial contact with the ground because the cap compressed once in contact with the ground and bounced slightly. If I were to redo this video, it would be more accurate from a closer distance so that I could better track the first initial contact the cap makes with the ground. And that's it. Thank you for watching my video.